Hi there, my name's Nigel Bayliss. I'm the Optimizer Product Manager, and the purpose of this deck is to introduce you to the latest enhancements of SQL Plan Management. And I'll be going through Oracle Database 19C all the way through to 23C. And then before we get going, we're just going to talk about some concepts that are important to be aware of. So there's a quick recap of that, and then we'll get on to the detail of what the enhancements are exactly. So what problem does SQL Plan Management resolve? It came in with Oracle Database 11G, so it's been around a long time. So I'll just cover some of the key ideas behind it. First concept to be aware of is that SQL statement performance is very dependent on the SQL execution plan that we use internally to execute the query. So it's the job of the optimizer to figure out an optimum SQL execution plan, and then ultimately the query is executed. So the key step really is figuring out what is the most optimum execution plan to use. Execution plans change over time, and they should. I think one of the key misunderstandings really with execution plan is that there's one that is discovered and that is good for all time. But that isn't always the case. In fact, it's probably rarely the case. We expect execution plans to change over time because the data changes, the data distribution changes. You'll have changes to the schema probably, and add or take away indexes, for example. All these things can induce plan changes. So it's normal for that to happen. So I think one of the key mistakes, if you like, is to start with thinking what I need to do is to make a plan never change. I want it frozen for all time and it will always be good. I mean, sometimes that is the case, but in the general case, it's unwise to think of it in those terms, I would say. So sometimes an execution plan, when it changes, will improve performance, and hopefully that's usually what happens. Of course, that's not something that's generally noticed. That's something, the database is expected to do. Sometimes it will degrade performance to a greater or lesser extent. And that can happen. Queries are complex. There's a lot of reasons why that can happen. So it is something that can happen. So there is a set of plan changes which can cause performance degradation. And then beyond that, there's a set of those performance degradations that affect the service level of the application. They don't go unnoticed. So of course you can have the case where the performance of a SQL statement degrades, but it's not in a critical section of the workflow or anything like that, and it's just not noticed. So there's the ones we're really concerned about, I would say, are where plans change, the performance then affects the service level, and that's what we want to prevent. So the way that we do this is to control SQL execution plans, have a mechanism for controlling them, and that is the SQL plan baseline. So SQL plan baselines are data, metadata, if you like, that's in the database that hold information about how the SQL statement plan is put together. So we store that in the data dictionary, and essentially it's a list of approved or accepted execution plans. So the SQL statements, we have a SQL plan baseline, and it says this SQL statement should use this plan. There's a slight complication to this in that SQL statements are allowed to have multiple execution plans, and there are often good reasons for that. But it's something, probably a detail we can ignore for now. So we just bear with the idea that the SQL statement has an accepted plan. The SQL plan baseline says you can use this plan SQL statement. And then if there's a plan that the optimizer comes up with that's different from that, the SQL plan baselines can prevent that plan from being used. So in this case, we have one plan that's allowed and one plan that's disallowed because it's not part of the accepted SQL plan baseline. So what does it look like? Well, SQL plan baselines, as I mentioned, are stored in the data dictionary, and we have to capture them. So the way that works, there's lots of different ways of capturing the SQL statement and their execution plans. You can take them from different sources like AWR, from the cursor cache, and in fact automatically as well. So there's a question here about, do I capture all my SQL statements or some kind of subset, for example, a critical core of SQL statements. I'll come back to this in a minute, but it's an important idea. But basically, we can concentrate on the concept that SQL plan baselines have a list of accepted plans. So that they tell, for the SQL statements we've captured and the plans we've captured as baselines, these are the ones that we're allowed to use by the optimizer. So the optimizer is prevented from using plans that deviate from the ones that we've accepted. So this is what happens in real life. The SQL statement is passed, and the optimizer thinks that a better plan is better, and it may well be right. However, we're not going to let the optimizer use that right away. So essentially what we do is we note the fact that a new plan has been created for the SQL statement, and we're going to remember that. So essentially it becomes part of the SQL plan history, or another way of thinking it is like a SQL plan baseline that's not yet been accepted. So the SQL statement, optimizer thinks it's got a better plan. However, we're not going to allow the optimizer to use that yet. We just remember the fact that that's happened, and then we use an accepted plan instead. So what we've really done here is the SQL statement has come in. We've arrested the optimizer and said, hold on, you can't use that plan yet because we don't know whether it's better or not. And so we've held that, and then we've used one of the accepted plans instead. So nothing's from the outside, nothing's really changed. The application sees the same thing and it moves along as normal. But this plan might be better. And as I said to you earlier, often it is a good idea to at least allow a plan to change over time. So what SQL plan management allows us to do is in the background to test the SQL statements that have got new potential plans and figure out whether those plans are better or not. So this is part of an evolution or evolve advisor task. It's something that happens in the back end. It starts up and figures out by test executing the queries whether the new plan is better or not. Pretty much as simple as that. And if it is, then it gets accepted and it becomes part of the SQL plan baseline. So the life cycle looks like this. There's a capture phase where we capture what we want to control. We accept a set of plans that we want used. And generally speaking, what you capture is what you accept. And then from then on, we're going to be enforcing those execution plans. And along the time, if there are any new plans are found, we capture those and figure out whether they should be evolved or used because they perform better than the older plans. So that's the life cycle. One thing that is important about this is the capture phase. Now, the question is, do we capture everything? Do we capture critical workloads? We can, in fact, if we want, even capture plans in a pre-production environment and export and import those SQL plan baselines into production. Should we just pick problem SQL only? So in other words, we don't create baselines unless we identify a SQL statement that has a problem and then we create a baseline for it. That's an extremely common pattern that you see. That's used very often. But this implies that there needs to be some kind of thought behind this. Do we capture always? Do we have some kind of periodic schedule where we do that? Or do we include it as part of the release cycle, where we release new queries, new code? Do we then effectively release plans as well? So the issue with this really, it's somewhat non-autonomous because you kind of got to figure out what you want to do and when. And to some extent, it needs knowledge of how you manage the application. That's the best way really to decide when to capture. It's driven by business requirement really and the way the application is used. So what we'd like to do is to come up with a more autonomous way of doing something that doesn't require this kind of decision making. So this is where the enhanced automation comes in. Now, just to make it absolutely clear, this is Oracle Autonomous Database and Oracle Exadata feature. It's in Oracle Database 19c. So this is available now. So I'll go through this and then we'll talk about 23c as well. Without if we imagine now the sort of more manual process, let's just take a step back really and think about how you might do this manually. And this, again, this is very commonly done. This is a very common kind of use case. So this is fully manual. A SQL statement has been executing for many days, months, years, and you haven't got a SQL plan baseline. Everything's fine. And then for whatever reason, one day the execution plan changes and it results in an increased elapsed time. And we're not lucky in this case. The service levels are compromised because this query is taking a lot longer. Now manual intervention begins and a repair strategy is identified, which this can take a while, of course. And then we implement the repair, whatever that is, and then the service is resumed. So this is, as I say, commonly done. And so why don't we think about removing the manual aspects of this and look at delivering something like this more automatically, something that requires no intervention. So this is what is behind the autonomous database features, Exadata features as well, where we have automatic SQL plan management. So here we're going to manage a SQL statements execution plan only if a performance issue has been established. So in other words, we're not creating or capturing SQL plan baselines in advance. We are essentially creating them as needed, rather like that manual approach. So in other words, we'll get the database to figure out whether there's been a SQL performance regression or not. We might get the database to do that for us. So we want that to be done automatically. We want to identify the SQL performance problem. And then if a previous execution plan exists for that SQL statement that is suffering from a performance issue, why don't we look back at those execution plans and figure out which ones we should perhaps continue to keep using. And then essentially what we can do is repair our SQL statement, if you like, by saying, actually, this previous plan we used is known good. Let's put that one back, constrain the optimizer so that it uses that plan going forward. So that's essentially delivering a timely repair, something that can happen theoretically much more quickly and certainly automatically without any intervention. So let's just take a closer look at this step here. How does the database know that a SQL statement is one we've seen before, and also whether or not the plan has changed and whether there's another plan available or not? How does it figure that out? All right, there's actually an infrastructure component that we introduced in Oracle Database 19c, and you can use this in Enterprise Edition as well. And it's called the Automatic SQL Tuning Set. The idea behind this is that we automatically maintain a repository of SQL statements that have been executed on the database. Basically, we remember the SQL, remember the performance it had, and we also remember the execution plans it had. So we remember all the plans that have happened to SQL statements. And I guess you can think of it a little bit like the AWR, the Automatic Workload Repository, that keeps a log of the top SQL in the database, whereas here we're looking at all the SQL. We're basically remembering everything. So it's maintained automatically. Again, it doesn't require any manual intervention, but it gives us a mechanism to identify where queries are new and where plans have changed. So that's its key purpose in this case. Interestingly, I mean, it was originally established as part of the automatic indexing autonomous processes. It was originally designed for that, and then of course we've now extended where it can be used, because it's a great resource to have, because it tells you what's been happening to the database over time. So there's some exclusions there. We don't capture everything. There's some throttling in there, so we don't capture large quantities of dynamic SQL, and also SQL that we've only seen executed, more than a year ago. We start purging those away, so it won't grow indefinitely for those reasons. So this is the flow. So this is automatic SQL plan management, and this is background verification, which I'll clarify in a minute. So essentially what we have is the evolve task. Remember that we have the evolve task which can execute, and it can introspect the existing automatic workload repository and the automatic SQL tuning set. It then is able to find alternative plans in the automatic SQL tuning set that we've captured over time. And we can test execute the SQL statement with those different plans. And if we find a plan is proven to be better, we can instantiate that. We can say to the optimizer, this is the plan we want to use. Let's reinstate a plan that has stopped being used, for example. And to do that, we'll create a SQL plan baseline. So basically, you end up then with a repository of the best plans. So what it's doing is it's targeting where an issue is seen, creating the SQL plan baselines to address those individual issues. As I say, this is all fully automatic, and it kind of apes that manual process you have, which is a sort of detect and repair. But in this case, of course, it takes care of it for you. I mentioned the background, and that's because this is a background task. So the Evolve Advisor is something that runs periodically. So in other words, you've got a process that wakes up, looks for these issues, repairs them, and goes back to sleep. So this is kind of wake and sleep. So is there something we can do that improves upon that? So this is where we can look at Oracle Database 23C now. Again, autonomous, Exadata, and now we're looking at resolving issues even faster. So how do we go about that? So what we can do, in fact, now, because we have the automatic SQL tuning set, we can essentially look when a query comes in, is parsed and executed, we can look at that immediately. So what we do is in the foreground, and I mean by the foreground, it's the process that executes the query, the actual application process that is executing that query or SQL statement. We can see that SQL statement and detect whether it's new. We can also detect whether it's got other plans or not. So when that SQL statement executes, we know now whether it has a new plan or not. Now, if it does have a new plan, once execution is completed, we can now say, was a previous plan better or not? So this is happening now in real time, so to speak. You're executing the query, and now we can look to see, was this query executing well or not compared to previous example plans that it's had. If it's not working well, we are now in a position again to fix that or repair it using a previous execution plan that we have in our SQL tuning set. So if you like, this is what it looks like. Execution, a SQL statement comes in, we hard parse it. We know straight away whether it's a new query or not. We also know whether it is a new plan or not. So we know that straight away. So we know if it's a new plan and a query we've seen before, once it's complete, we can figure out, did this plan perform well or not when set against the other plans that we know about? We're immediately in position to know that. So the full life cycle, if you like, is we get the SQL statement come in, we compare against the automatic SQL tuning set, all happening in the foreground. And then if we establish that, in fact, a different SQL execution plan should be used, we can enforce that by creating a SQL plan baseline for it. So all of this happens in the foreground in a line, so to speak, one after another, and something we can take care of immediately. So what's happening here is the SQL statement executes, we see a problem, we repair the plan, and then the next time it executes, it's going to be using the more optimal plan that we've previously used. So I did mention this a little bit earlier, I alluded to this, is that these enhancements we've added change quite a lot of functionality under the covers and add new things. And that means you can leverage that. In fact, in this case, you can make use of some of these changes that we've made. In particular, you can enable the automatic SQL tuning set on Enterprise Edition, for example. You can start that off and allow it to collect this history of execution plans and SQL statements over time. If you do that, and you encounter an issue with a SQL statement where the performance is not good, you can now use the Evolve Advisor to go and look in the SQL tuning set and figure out whether it can repair that execution plan from the previous one that it knows about. So it's not end-to-end automated, but if you discover a SQL statement that has an issue, you can point the Evolve Advisor at it and say, figure out what to do about this execution plan. So now it can go and look in this repository of data, the SQL tuning set, the auto SQL tuning set, and figure out how to repair the query or SQL statement for you to fix the plan, basically. Okay, so that's something to definitely bear in mind if you're using non-autonomous or non-Exadata systems. So summary, automatic SQL plan management detects execution plan changes. That's its key thing. And then once it's done that, it can establish whether that plan is an improvement or regression in performance from what came before. And it does that depending on whether you use the foreground or background. It can do that in either the foreground or the background. You can choose. If it establishes that there's been a performance regression, it can reinstate a previous plan. And now there could be multiple plans, but it will pick the one that it considers the best out of the ones that were used before. Fully automated, you don't need to kind of establish, for example, a capture cycle or anything like that. You can just let it take care of the database for you in an autonomous fashion, basically. For more information, I look after the Oracle Optimizer blog. There are some articles on there that are specifically about this, so I've left you a couple of links here. So it talks about the SQL tuning set and also about the process of the automatic SQL plan management, which is currently 19C and will be updated to 23C soon, of course. So I'd like to thank you. I hope you found that interesting. Thank you for listening to the talk, and I'll speak to you again soon. Thank you.